Hey everybody, so this is a video for Module 2, Topic 2, Lesson 1, which is on page 333, which is for Algebra 2, Day 8. So I'm going to go through a few examples of this lesson. The learning goals is to use polynomial identities to rewrite numeric expressions and use polynomial identities to generate Pythagorean triples, and identify patterns in number generated from polynomial identities. And then prove some statements using polynomials. Okay, so I'm going to jump ahead to the first activity. So in the getting started, what you're going to do is you are going to write an equivalent relationship for each of these. So we got a plus b quantity squared, a minus b quantity squared, a plus b quantity cubed, a minus b cubed, etc. So some of these, like c and f and g, can be factored, while the rest of them can be multiplied out. Now, if you go on to the next page, the activity, they actually have all of these pretty much worked out. And these are what we're going to use to evaluate numerical expressions in a different way. Okay, so we have 46 squared. Well, I know that you can just take 46 and multiply it times 46, or use a calculator and do 46 squared, but we want to look at it in a different way. We want to look at it as a sum of 40 plus 6 quantities squared. So let's look at the example, and then we're going to try another way of doing 46 squared. So if we think of it as a sum as 40 plus 6 squared, what we're essentially going to do is we can think of it as an a plus b quantity squared. So a is actually 40, and we're going to plug a in with 40, and b we're going to replace as 6. So you can see over here we are applying the polynomial identity. So the 40 is here and here, the 6 is here and here. And then from there we're doing a calculation of 40 squared is 1600. 6 squared is 36. 2 times 40 times 6 is 480, and then you add them all up. So this one says calculate 46 squared in a different way by writing 46 as the difference of two integers squared. So the last one was a sum. We can take 46 and think of it as a difference. So the easiest number that, you can do a lot of things, subtract to be 46, but you want to think in terms of a number in like the tens, like 40. So in this case, I'm going to do 50. And then what would I need to subtract to get 46? That'd be 4. So 46 squared is equivalent to 50 minus 4 squared. So the reason that we want that 50 is because it's easy to square in our head 50. 50 times 50 is 2,500. It's pretty easy to do that in your head. Okay, so I'm going to use the identity right here. A squared minus 2ab plus b squared. Okay, so let me write that down. A minus b squared equals a squared minus 2ab plus b squared. Okay, so my a is 50, and I'm going to substitute it into the formula here and here. And my b is 4, substitute it in here and here. So let's see what it looks like. It'd be 50 squared minus 2 times 50 times 4 plus 4 squared. So the benefit of using this formula is these are easier things to square. 50 squared is, well, 5 squared is 25, and then you put 2 zeros at the end of it. 2 times 50 is 100, times 4 is 400. And then 4 squared is 16. Okay, I could do a little subtraction here. 2500 minus 400 is 2100. Plus 16 gives me 2116. Okay, I'm going to do one on the next page with a cube. I'm going to do B, 27 cube. So now we can use one of the cubic formulas. 27 cubed, we could use A minus, we could do 30 minus 3 cubed and use this formula. Okay, so that formula is A minus B. So let me write down the formula we're going to use. A minus B quantity cubed equals A minus B times A squared plus A times B plus B squared. Wait, no, I think I'm missing a 2 there. Minus 2. Okay. Let me just double check my formula. All right, looks good. Now I got the formula. Now I'm going to substitute things in. Oh, first I have to write 27 as the difference, 30 minus 3. So it's going to, let's put everything in the right place. A is going to go here, here, here. So I'm going to put here, here, here. It's 30. 30 squared minus 2 times 30 times B, B squared. Okay, we need a B. B is 3. So we go here, here, here. So minus 3, 3, 3. Okay, now let's clean it up. This parentheses is 30 minus 3, which is 27. Actually, that's just going to give us some ugly stuff. So I think let's try to keep it nice. So let me show you how we could simplify this in a way that's going to be a little nicer. We're going to clean up the second parentheses first. So 30 squared we could do is 900. 2 times 30 times 3 is 180. And 3 squared is 9. Okay, we could multiply by 27, we could do this, but one thing that you can do is you could choose to, we want to keep things with zeros as much as possible. So by subtracting 30 minus 3, I'm going to end up with 27, which is now hard to multiply again. We're trying to make things so that we can do them in our head without using a calculator. Because if we were using a calculator, why wouldn't we just do 27 cubed in the begin with? We're trying to learn more mental math tricks, basically. So we can do 30 times 90 pretty easily, or 900. 30 times negative 180. And do 30 times 9. All of these I can pretty much do in my head if you've got your times tables down pretty well. Okay, now I'm going to do negative 3 times all of these things. So I'm basically doing long foiling where you got 2 things and 3 things. It's like distribution. So I'm going to do negative 3 times 900. And then a negative times a negative will be a positive. And then 3 times 180. And then negative 3 times 9. So it looks like a lot more multiplication, but we can do all of this in our heads. 3 times 9 is 27, and then just put all the zeros at the end, so 27,000. 3 times 18 is 54, and then again put the 2 zeros at the end. 3 times 9 is 270. 3 times 900 is 27 plus 2 zeros. 3 times 180 is 540. And And then 3 times 9 is 27. Okay, then from there we can add and subtract. And you get 19,683. Okay, I'm going to jump ahead to talking about Pythagorean triples and how we can generate them using a formula. So Pythagorean theorem, remember the Pythagorean theorem? You got a right triangle, you got a leg, and a hypotenuse. And so the leg is sometimes A and the other leg is B, and then the hypotenuse is C, and you get the equation A squared plus B squared equals C squared. So sometimes when all three of those numbers are integers, you get what's known as a Pythagorean triple. So you can determine whether something is a set of numbers that is a Pythagorean triple by taking the numbers. The largest one will be the hypotenuse. So if I have 4, 5, and 9, I can use that as C, and I can check. Well, they're all integers, which is lovely, but do they fit into the Pythagorean theorem? 4 squared plus 5 squared, does it equal 9 squared? 4 squared is 16. 5 squared is 25. And 9 squared is 81, and hopefully you can see 16 plus 25 does not equal 81. So this is not a Pythagorean triple. If it has decimals, it's not a Pythagorean triple because they have to be 3 positive integers. Some famous Pythagorean triples. The 3, 4, 5 is very famous because 3 squared plus 4 squared is equal to 5 squared. So that's 9 plus 16 equals 25. And you can see that it works. Okay, so let's talk about Euclid's formula. So Euclid was a mathematician. He did a lot of things in geometry and in mathematics in general. And so he came up with this formula to generate Pythagorean triples given any two positive integers, r and s, where r is greater than s. Okay, so we've got r squared plus s squared quantity squared equals r squared minus s squared quantity squared plus 2 times rs squared. And so this first part gives you the hypotenuse, c squared. It gives you c squared. This gives you one of the legs squared, and this gives you the other leg squared. Okay, so let's try it out. Let's look at the example. And we can also look to see why it works. You do a bunch of algebra, and you'll see that it is true on both sides of the equation. So anytime you're given a formula and you want to verify that it's true, you have to manipulate one side to make it look like the other side. So we have this right-hand side. We need to make it look like the left-hand side. So let's FOIL some stuff out, or let's use some identities. So this is similar to a minus b squared, except these are squared. So your powers are going to be higher. So the formula without those little squares, okay, was a squared minus 2ab plus b squared. What's going to happen if you do a squared is now this is a to the 4th because it's a squared squared. This is a squared. And if b is squared, that's going to turn into a little squared, and that's going to become a 4th. So you can see that's right here. Okay, then we have 2 times a times b, all quantity squared. You can square all of those because they're in parentheses, and you get this, 4a squared b squared. Now you can do a little combining like terms. These are like terms, the a squared b squared terms. And then this basically turns into what you would get when you use that. That's kind of like this same formula, except a plus, which turns this into a plus. So they just used it backwards to show that it works. All right, so let's practice using this Pythagorean triple generating theorem. Choose two integers and use them. Okay, remember that r has to be greater than s. Okay, I'm going to use r is 4 and s is 3. Okay, so r is bigger than s, right? Let's look at our formula again. Okay, let me write it all down. R squared plus s squared squared equals r squared minus s squared squared minus 2 times r times s quantity squared, right? No, sorry, plus, not minus. There we go. So let's substitute and see what we get. All right, I'm going to plug in 4 and 3. 4 for r, 3 for s. 4 for r, 3 for s. And let's do a little math and see what we get. Now, remember that we're looking for c squared, a squared, b squared. This part inside the parentheses is essentially what c is, because the whole thing is c squared. So you can kind of ignore the square there. So really, I just want to look at this part. Okay, 4 squared is 16 plus 9. That gives me 25 squared. Okay, I'm not going to go ahead and square that. We don't need to do the last square, really. Okay, then we've got 4 squared minus 3 squared, which would be 16 minus 9 squared, which is 7. And then last, we've got 2 times 4 times 3. 2 times 4 is 8. 8 times 3 is 24. So my Pythagorean triple here that I got is 7, 24, and 25. Just in order from least to greatest. So you see the 25 was the hypotenuse, 7 and 24. And you can verify this. This is 625, this is 49, and I believe this is 576. So if you add 576 to 49, you will indeed get 625. So we can verify that it does work. So come up with your own Pythagorean triples. Okay. All right. We're going to do one more problem. And we're going to practice proving from activity 3, proving a polynomial identity. And it's a lot of just manipulation and algebra. So to verify each algebraic statement by transforming one side of the equation to show that it is equivalent to the other side of the equation. So I'll do number 1. Let's see. We're going to have to do some foiling, distribution, lots of stuff. So we are going to start with the right-hand side, and we're going to FOIL and multiply some stuff out. And hopefully by the end of it, we should get v's to the 6th minus w to the 6th to show that it worked. All right, so I'm gonna start with a little bit of distribution here. I'm gonna multiply the first two sets of parentheses. Now, you can distribute, like distribute the v squared and then distribute the negative w squared. You can also choose to use a grid to help you. In this case, I have 2 terms by 3 terms, so you can do a 2 by 3 grid. So I have v squared minus w squared, and then the 3 terms in the other polynomial are v squared minus vw, and then a w squared. So I like the grid. That's just me. Helps me keep track. So v squared times v squared is v to the 4th. Remember, when you're multiplying something of the same base, you add the exponents. Then we have v squared minus vw. It's going to be negative, and this v is going to, the exponent's going to add, and you're going to get v to the 3rd, and then there's a w. And then v squared and w squared, they're different bases, so you're just going to write v squared w squared. All right, now the bottom row, negative w squared times negative v squared, so it's going to be negative v squared w squared. And then the middle one, a negative times a negative is a positive. There's only one v, and then I have w cubed. And then last but not least, we've got a negative w to the 4th. Okay, we're going to look to see if we have any like terms. And we do. We can cancel some. Do you see the v squared w squared and the negative v squared w squared? Those are opposites, and they're exactly the same. They're going to cancel out. All right, so let's write down what we have. We have a v to the 4th minus v cubed w plus vw cubed minus w to the 4th. All right, I still have this guy, and I'm going to have to do another multiplication. If you like the grid, you could use the grid again, except you're going to have to make a pretty big grid because it's 1, 2, 3, 4 times 1, 2, 3. Okay, you'd have to make a 4 by 3 grid. That's getting a little bit too big for my taste. So in this part, I'm going to use distribution. Okay, so you know, I don't know. Maybe the grid would be best. It's up to you how you want to do it. If you were going to use distribution, you would distribute the v to the 4th to everything over here. Then you do the second term to everything over here. Then you do the third term, etc. I'm going to use a grid. I already drew it. I'm going to use a grid. So I have v to the 4th minus v cubed w, vw cubed minus w to the 4th, and then the 3 from over on the right here. All right, I'm gonna get at it. Hopefully some stuff is gonna cancel because this is a mess. V squared times v to the 4th is v to the 6th. Okay. Just keep in mind that if you have the same variable, you're going to add the exponents. So when I see v squared and negative v to the 3rd, I'm going to have a negative. And I have a bunch of e's, so add the exponents to the 5th, and then just tag along the other letter. Okay, I'm going to ask you to try and finish this. Fill out the rest of the grid or do the distribution, whichever method you like. And then when you're ready, unpause it, and you can see if you got it right. Okay, I haven't combined like terms yet, but here are my terms in my grid here. Okay, this is gonna be a little confusing with all these V's and W's, but you wanna look for like terms, and you wanna with those like terms, they need to have the same combination of variables and exponents. So for example, v to the fifth w, this negative v to the fifth w, there's another v to the fifth w right here. They're opposites and they will completely cancel each other. Ooh, canceling is fun. Okay, what else we got? V cubed w cubed. Ooh, I see a negative v cubed w cubed right here. But bam, it's gone. All right, I've got a negative v squared w to the fourth. I'm looking for a v squared. Oh, right here, v squared w to the fourth. They're opposites. Oh, everything's canceling. This is amazing. Okay, negative v to the fourth w squared. Oh, right there, v to the fourth w squared. It cancels. And our last one, negative v to the fifth. Oops, I made a mistake here. This is supposed to be a fifth. I made a mistake. I was like, it's not going to cancel. Oh, wait, no, I made a mistake. Now it's going to cancel. And all of that turns into v to the sixth minus w to the sixth. There it is. Look, it worked. But bam, you proved it. This is kind of an algebraic proof. All right. Go ahead and finish up the rest of this lesson on your own. Use that answer key to help you and to check your answers, and go from there. You also do have a Mathia. The Mathia is, let's go ahead and find what that Mathia is. One sec. So the day 8B Mathia is on three things: Pascal's triangle, binomial theorem, and exploring polynomial regression. So these are all, well, the first one here, you can see Pascal's triangle. This is a content builder, so just learn about the Pascal's triangle through the lesson, okay? They'll basically teach you about all the cool things and patterns of Pascal's triangle. And then we have the binomial theorem. This workspace is also a workspace that will help you learn about it. You're also going to have to do some combinations. Combinations is necessary to understand Pascal's triangle as well. And there's a formula for combinations. This exclamation point is a factorial. It means that you are going to multiply a number times all the numbers below it. So like 5 factorial is 1 times 2 times 3 times 4 times 5. Okay, so if I'm finding the combination of 4 things from 6, your top number, you see the n and the k, it's just a formula. So 6 goes up here, and then it's 4 factorial times, and then you subtract them. If you look at the formula, it's n minus k in there. So 6 minus 4, or just 2. Okay, and so what does this say? All right, well, let me write down this on paper and I can work it out for you to show you how you can work it out. Okay, so this is what we came up with. So how do we figure out where to go from there? 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. So that's what a factorial is. You're multiplying all the positive integers from that number down to 1. 4 factorial is 4 times 3 times 2 times 1. And then 2 factorial is 2 times 1. And then you can see that there's a lot of stuff that we can kind of cancel from there, right? We can cancel 4, 3, 2, 1. We can cancel 2, goes into 6 3 times. But let's look back here and see what our options were. Okay, let's see. The only one that actually worked if we kind of compare them, let me kind of back up a little bit. So before I did that last part with the 3, I had this 6 times 5 on the top, 2 times 1 on the top, and the 4, 3, 2, 1 cancels. So they did have an option that looked like this, which is true. That works. So that's the one I'm going to pick. Okay. And then you can go ahead and continue on from there. I'll post some extra videos about the binomial theorem. I don't have the time to make a new one just for that, but I can give you some extra resources that you can look at. And then your last Mathia assignment, let's go ahead and take a look at the last Mathia assignment. There's 3 workspaces. The third one is exploring polynomial regression. So let's take a look at that one. So polynomial regression. So a regression equation is a function that models the relationship between 2 variables in a scatter plot. So you've done linear regression. That's where you try to make a scatter plot and you can see that it looks like a line, and you try to make the regression equation for the line. You may have even done quadratic regression or exponential regression. So here is polynomial regression, where you're looking at data and trying to match it to some sort of polynomial function. Okay, so this is also a concept builder. They're not the mastery workspaces. You're just learning about the concepts in these 3. They shouldn't take you too long. They said the first one should be about 12 to 17 minutes, the binomial theorem about 13 to 20 minutes, and the last one about 8 to 13 minutes. All right, I hope this helps you out for today's work. Good luck.